Welcome to an exciting year in pre-AP chemistry for Westlake High School. This is going to be the first of many videos that you will see posted. Hopefully these help you throughout the year if you happen to miss class or just need a little bit of extra something to understand the concepts. We are starting off with calculations and measurements that are used in chemistry, and as part of that I thought we'd start off with something, the little eye-catching dead baby rule. And when we look at how we report certain numbers, this is going to be something we want to keep in mind. And let me start off with the example of many years ago. There's a substance known as heparin, and it was, I think it's a blood thinner, and it was used with uh, in hospitals, and some nurses, when they're trying to read either a doctor's handwriting or maybe it was in triplicate form, and by the time they were able to look at their copy that they had, it was a little bit illegible. And suppose we have a number like this, that they need to administer 0.5 cc's of heparin. Well, you can probably see where this is going. If it's not real visible, they might look at that and just see that as 5 cc's, 5 cubic centimeters of heparin. Well, if they're trying to administer that to a little tiny infant, 0.5 is the proper dosage, 5 is way too much, and then so quite a few babies were actually killed that way. So it's one of the things that we want to do to avoid that type of misconception is that we want to make sure that whenever you've got that decimal in front with no other numbers that are significant value numbers, that we want to go ahead and put a 0 in front of that decimal point, and then that way there are no questions about what that value is. So the proper way to write that is 0.5 cc's is a much better way than just saying 0.5, because that way it makes it much clearer. Okay, so that's the first thing we want to look at. Then we want to look into some definitions. We have, when we're looking at numbers, we want to think about what those numbers mean. We want to look at the accuracy of something and also the precision of something. So there's a space on your notes. These videos are always going to be customized to your notes that you receive in class. So the first thing we want to think about is what accuracy is. That is how close a measured value is to an accepted value. So in order to be able to judge how close it is, you actually have to know what the accepted value is. If I said the lifespan of a squirrel is 9 years, well, who really knows? You have to know the real value. That might be accurate, it might not be, but you have to know the real value. Another thing we can think about when we look at accuracy, because it's how close it is to a measured value or an accepted value, if we considered a dartboard, then if I got 3 of my darts right there, I would say I'm pretty darn accurate. Even if I got my darts to be here, here, and here, I'm still fairly accurate. So again, it's how close it is to the measured or accepted value. If you're playing darts, then the bullseye is where you want to get your darts to. And then, of course, precision is going to be how close a series of measurements are to one another. So in this case, this really goes back to what our equipment is. Precision is going to be dictated by the type of equipment that you use. Here we have 2 different pieces of equipment. Hopefully, you guys know from previous science classes that this would be a beaker, and here we have a graduated cylinder. So in this case, one of these is used just really for holding liquids of some sort as a containment vessel. That would be your beaker. The graduated cylinder is really, the purpose of it is to measure the volume of a liquid. So this is the one that we're going to use as our graduated cylinder. And the reason being that our values are incremented differently. They're more specific. We've got more tick marks on there that allow us better precision with our measurements. If we were to relate this to a dartboard, we could say that if you get your 3 darts right here on the wall, yeah, you're pretty precise, but you're not very accurate. So I believe you have a little diagram on your notes as well that kind of helps with some of those things. Okay, so now we get to the idea that there are different numbers that we're going to be using in chemistry. And There are two main types. We're going to say that there's exact numbers and there are inexact numbers. An exact number would be something like the fact that there's 12 eggs in a dozen. Most people have exactly 10 fingers and 10 toes. Even if I said something like, hey, I have 30 people in this room, that's an exact count. Or in these cases, some of these other examples, they're conversion factors. So counts and conversion factors, maybe we should summarize that. Counts and conversion factors are always going to be considered exact numbers. In other words, what that means is when we start doing some math with these, and I know we haven't really defined this term yet, but when we start doing some math with these, we're going to see that exact numbers do not affect our number of digits that we use to report our values. We don't use those to limit our values in our answer. Okay, so now moving on to inexact numbers. If I were to use a graduated cylinder that's a 10 milliliter graduated cylinder, or if I use a graduated cylinder that's a 100 milliliter graduated cylinder, if you were to look at those graduated cylinders, you would see that they are incremented differently. And because of that, if I tried to, if I used a 10 mil, I might be able to get a volume of 8.81, but if I used 100 milliliter, I might only be able to get it to a precision of 8.7, let's say. So you get different precision based on the equipment that you used. And again, this is going to be for measured values. And that's really what we're going to be talking about a lot in chemistry. Whether we measure them or we're just looking at some numbers on a paper that were measured, that's what we're going to be looking at. Now, what this means is that it conveys the quality of the measurement, therefore the quality of your measuring device, what type of equipment you used. If you use your bathroom scale, you're probably not going to get a very precise measurement for the amount of substance that you're using in lab. But if you're using our electronic balances that report out to the hundredths place, you're going to get a much more precise measurement. And we control this when we're working with these values and calculations. We control the number of number of digits, which is our significant figures, when reporting these values to ensure that the measurement does not appear to be more or less precise than the equipment used actually allows. Okay, so we're going to keep stressing this. So now there's a place for you to fill this in. What exactly are significant figures? We brought that up a couple times now. Here's what you need to write down. They are numbers in a measurement that include all of the digits that are known plus at least a digit that is estimated. And it's that last digit, plus a last digit that is estimated. Numbers in a measurement that include all of the digits that are known plus a last digit that is estimated. Let's think of an example that we've, I guess years are going by. This might not be the best example, but I think a lot of you can still probably remember this. Why might have this been important in this situation? Well, here we have Mr. Phelps. Prior to 1972, if he had swum in that Olympics, where the equipment only measured precision to the tenths of seconds, he and, of course I forget the guy who came in second place, he's never remembered, is he? It would have been a tie because it was only measured to the tenths of a second. However, Michael Phelps did win that because the precision of the equipment allowed it to be measured to the hundredths of a second, so therefore he won by like 1/100th of a second, and he was able to win that. Okay, so let's look at an example. You don't have this on your notes, but you can just follow along. Here I have this piece of metal. And what I want to do is I want to figure out, based on this ruler that I have, well, this is a pretty bad ruler, you can see, what distances can you be certain of on the ruler in Model 1? In other words, what is the distance of this piece of metal? What can you be certain of? Well, I'm going to go ahead and answer that. It's going to be greater than 0, we know that, and I'll even put my units in there. Greater than 0 centimeters. We also know it is less than 10 centimeters. That's really all that ruler allows us to look at because of those little increments, those marks on there. Here it says it's not very useful. but a measurement can be estimated. How might you divide up the ruler by eye in order to get the measurement? Well, I think most of us could probably look at this and go, well, yeah, I can visualize where that halfway point is. So there's our 5. Maybe you'd say something like it's around 3 centimeters. You could probably get pretty creative and try and figure out some other ideas on how you can do that. But what we get out of this is that it's not a very precise piece of measuring equipment. It's not a very good tool. Well, let's look at our next model. What if we had that same ruler, but now it's got more tick marks on there? We've got it by ones. Instead of just ticked off by 10 centimeters, it's ticked off by 1 centimeter marks. So here it says the students obtained a better ruler. What distances can you be certain of on this ruler? Again, we're trying to measure this piece of metal right here. So I can count this off. I know I've got 0, 1, 2, 3. Well, I can look at this and say, yeah, it's going to be greater than 3 centimeters. I can't write. Greater than 3 centimeters and less than, still can't write, less than 4 centimeters. That's what this piece of equipment allows us to say. Well, if we had some students and they were asked to go ahead and write down their measurements, their values for this, let's say that we've got all of these written down from these 6 students. The question is, were they able to agree on a single value for any of those digits? And we can see that the answer is yes. They all agreed that it is 3 or 3 point something. So they all agreed on that first digit in the tens place, I guess that is. So then the next question is, what feature of the ruler in Model 2 made it possible for the students to agree on a value in that digit? And it's the fact that it's got other lines of measurement in there. So it broke it down into smaller increments. So it made it a more precise piece of equipment. And again, we break this down even further. Same piece of metal. Here we've got our 3. Here we've got our 4. And just jumping down to the question, we've got our 6 students. And it says, were they able to agree on any of the values? Again, they all agreed on that 3. And because of this might be hard to see from where you're at, but here is the 2, 3.2, and then this is a 3.3. So some might say, yeah, it's just 3.2. Some might say it's 3.2 something. But they are all able to agree on those 2 digits. Which of the 6 values are valid and which ones are not? So here's what I want to address. I want us to, let me just go back really quickly to this definition. Remember, we said that significant figures are going to be numbers in a measurement and that include all of the digits that are known plus a last digit that is estimated. So what that means, when we go through this, that the 3 is definitely a known value. That 0.2 is definitely a known value. We see that it hits that 0.2. It's beyond that 0.2, or at least to that 0.2. So that's a known value. Then you have to eyeball it. You don't know how this one's incremented. Of course, I can't draw that in there, but if I tried to take between these 2 lines, these 2 points, and even divide it into tenths again, I can't really see that. So what do I have to do? I have to estimate it. So in order for me to report this to the correct number of sig figs, this piece of equipment and this the measurement for this one substance here to the correct number of sig figs, I have to report the 2 known digits in this case plus an estimated digit, so which is always going to be that last digit. So to say, there's that estimated 3.21, that's correct. That looks great. 3.20, yeah, that's valid. It's hard to read. Maybe it does just fall on that 0.2. 3.22, that could be true. That's about it, because now Mark's answer here of 3.2, he's not doing an estimated digit, so that's not valid. And then Emily and Dion, they are also trying to take it out to too many significant figures. This piece of equipment does not allow that much precision, so it's false precision. You're reporting something that is false because you don't know to that degree of precision what it is. Okay, so that's what we just answered there. Alrighty, so now this gets us back to counting significant figures. And what we end up seeing is that we have this list of rules. This is a fabulous way to learn significant figures, is you learn your rules, and they make sense. If you had a value, a measurement, 451, well, there aren't any zeros in there. Every single one of those digits is a significant figure or significant digit. Every single one of these is a significant figure. So you have 3 significant figures, because if it's a non-zero number, then it has been measured and it's significant. Our second one, if you have zeros in there, well, if they're sandwich zeros, in other words, they're between 2 non-zero numbers, again, they are significant. They are measured values. So this zero, these, all of those are going to be significant. So all you do is count up all of those digits. 3, 5, 5 significant figures. So it's pretty straightforward there. Here's where it starts getting tricky. If you have zeros that are leading zeros, so that's going to be when you have some decimal points, those are never significant. So this zero right here, even these zeros are not significant. So for example, if you had, let's say 6.4 kilometers, right? Well, that's the same exact thing as, let me rephrase that. Let me do something different. If you had 6.4 meters, that would be the exact same thing, and we'll look at how we go through this math later on, but that would be exactly the same thing as 0.0064 kilometers. So just because I'm converting between meters and kilometers, that doesn't mean that I should suddenly be more precise by having a greater number of significant figures. Those zeros in front are not significant. So there's our rule on that one. Okay, number 4. Trailing zeros can be significant, and they are significant only if the decimal point is present. So for example, here, this 0, this is that last estimated digit, so it is a significant figure. Here, this one's a measured value, this one was estimated. All of those are going to be significant, so you have 4 significant figures. But now, because we don't have a decimal point in this last one, the trailing zeros are not significant. There's only one significant figure in this. We'll do some examples. And as we said already, exact numbers have as many significant figures as needed. So these are counts, 26 students, 3 eggs. Don't worry about those. Those are just counts, and they're not going to limit your significant figures. They're infinite numbers. So for example, if we said we had 26 students in here, that's really not true. It is true, but you could think of it also as 26.00000. I don't see a fraction of anybody in here at all, so it could go on and on and on. You have an infinite number of significant figures. All right, those are our rules. Let's look if we can see if we can apply those to this. In our first example, we have, here it says, determine the number of significant figures in the following quantities. I want to address this really quickly. Quantities, that's what we use in chemistry. Very rarely do I just say, yeah, the answer is 16. It's going to be 16 centimeters, 16 milliliters. So quantities contain both a number and a unit. And you're going to find that if you do not report your answer as both a number and a unit, you will get points off throughout the year. So it's really important to report your answers in terms of quantities. Okay, so 3.82, 3, 8, and 2. So in this case, we have 3 significant figures. I'm actually doing this video without any students in my room right now at all, so I can't call on anybody to do this. I'm just going to keep going, but hopefully you guys can follow along and see what's going on. Again, here we've got 24, no zeros, so this is pretty straightforward. Both of those values are significant, so it's going to be two significant figures. Here we've got a couple zeros in there, but notice they are leading zeros. So think about what your rules tell you. Leading zeros are never, never, never significant. So in that case, there are three significant figures. Okay, here we have something we haven't talked about yet. It's actually at the end of the notes. But we know that this is in scientific notation in this problem right here. What we're going to see is that 2.1 times 10 to the fourth is exactly the same thing as taking that decimal and moving it 4 places to the right. So it's going to be 21000. Same thing. Doesn't matter how you're looking at this, 2.1 times 10 to the fourth or 21000. Both of those tell you the same thing. Here, let's look at it the way we've already talked about, that if you have trailing zeros but no decimal point, remember what that says, trailing zeros and no decimal point, you don't count those zeros, so you only have two significant figures. Here is a little hint for you. Whenever you're given something in scientific notation, this is what you look at to determine your significant figures. This never is significant, so that doesn't play a role in your significant figures at all. You've just got two. You're looking at that coefficient. All right, next one. Again, we have a zero that's there, but it's a trailing zero. So because of that, that means it's a measured value. So in this case, we have 5 significant figures. And last one, you're testing yourself hopefully, and you come up with the answer that there are 3 significant figures because there's no there's no decimal point with those trailing zeros. Okay, it is important that you learn those rules. That is really, really, really how I want you guys to learn significant figures. Now, with that said, I'm going to just jump into this really quickly, not spend much time. But there's also a quick way to remember this if you're just kind of trying to do that. You've got the idea down, you understand your rules, but you just want to think about this really quickly. You can remember your geography. You know that over here we have the Pacific Ocean. Over here, we have the Atlantic Ocean. So we're looking at Pacific and Atlantic. I'm just looking at my my map of the United States. Pacific and Atlantic, you can think of it as decimal point present or absent. So we're always going to start with our first non-zero and keep counting until we fall off. If there is a decimal point that is present, I'm going to start counting from this direction. If there's a decimal point that's absent, I'm going to start counting from the Atlantic. So in other words, that direction over there. If you want, feel free to skip through this part in the video. But here we go. I'm just going to do this one little example. It helps some people. Some people like to see this. So in this case, let me move this guy. Okay, so we've got the decimal point is present. So let's start counting from the Pacific at our first non-zero number and keep counting until we fall off. So I go to my first non-zero number, and here it is right there. And I keep counting until I fall off. So the answer is that there are 4 significant figures. Okay, let's do that with the next one. Here, my decimal point is absent. So I'm going to start counting from the Atlantic. Again, you always start counting at your first non-zero number, and here it is. And you keep counting until you fall off. So in this case, again, we have 4 significant figures. And last one. If we've got this guy, decimal point is present, so we come over here and start counting from the Pacific, and we start at our first non-zero number and keep counting until you fall off. So 1, 2, 3, 4, 5, 6, 7, 8 significant figures. If you like that way, great. If not, that's all right. Everybody should learn their rules. Okay, so now we go back to what you see on your notes. And here we have, this is just testing, just making sure that you know what you're looking at. And everybody knows that that is a graduated cylinder that we're using to measure volume of a liquid. And it says, how should you record the volume of the liquid? Well, first of all, everybody knows that you look at that, you've got that meniscus. You are going to read the bottom of that meniscus when you read that, and you get down at eye level when you read that. So here, yeah, I can see it's 40, and then I count 3. But is that all I'm going to say? I know it's 40 something. In fact, I know it's 43. Those are known digits. Based on this piece of equipment, I can also estimate my last digit. And I see that it lands smack dab on that line, so I'm going to say 43.0 milliliters. So again, this is where people make their mistakes. They forget to put in that last estimated digit. Lots of times, based on the equipment that you're using, it varies. But lots of times when you've got small little increments right next to each other like this, it's really just easy enough to say a 0.0 or a 0.5. It's hard to get too much more precise, but you can get in another estimated digit in there. So because of that, in this case, we look and we see that we recorded 3 significant figures. Okay, so in this one, we've got a ruler, and we just want to be able to say what those values are, A, B, and C. They're in centimeters. How would we record those measurements? So again, I'm looking at A right now, and I see I'm not going to say that because that would be killing babies. So I would say 0.7 centimeters. Okay, next one. We've got 1. Ooh, ooh, ooh. You know what? I just went too quickly. Sorry about that. 0.7, yeah, that's known. 0.70 centimeters. I did that just to make sure you guys were paying attention there at home. Next one, B. We see that, yeah, it's definitely 1 something centimeters. In fact, I can say 1.5. I know that. And then I'm looking and I think, wow, that's pretty, that's on that line. So again, 1.50 centimeters. And then the last one, C. Well, I know it's 2. I also know that it's, let me see if I can do a different color. 1, 2, 3, 4, 5, 6, 7, 8. Oh, but less than 9. So I know it's 2.8. And then I have to estimate that last digit. I'm going to call that 0.5, a 5, because it looks like it's halfway in between. So 2.85 centimeters is what I would call that. So in this case, we happen to see that the sig figs, this first one, we have 2 significant figures. Here we've got 3, and here we've got 3. What we notice on this is that this piece of equipment allows us to measure to the 100ths. Is what that allows us to be precise to, the 100ths. Okay, then we get to rounding. And for this, we've got some rules that you guys have probably used in your life already anyway. That if your numbers are between 0 and 4, just leave it alone. However, if it's 5 to 9, then you're going to raise it. You're going to increase it. So here is, I'm going to rewrite this number. 21.409653. There's our value. The first question says, hey, round this to 2 significant figures. And this is hard for me to do. I can cover my hand up in front of this, what I've written in blue, but you guys can't see that. But cover everything else up. Let me just erase. Let me not do that. Let me do 2.4. I'm going to erase everything but 3 significant figures. So now the question is, based on that, how would you round that to 2 sig figs? And the answer is 21.4 just becomes 21. If you wanted to keep that decimal in there, that would be just fine. It doesn't change it. That decimal in that case still keeps it at 2 significant figures in both cases. Well, what if we have, instead of rounding it to 2 sig figs, we want to round it to 3? Well, let's see what that 4th significant figure is. That 4th significant figure is that 4th digit is a 0. So we have 21.40. How do I round that to 3 sig figs? And the answer is 21.4. Notice that I didn't start at the very far right-hand side with the 3 and then go to the 5, then go to the 6, and think about rounding things up from there. All you do is use 1 extra digit and round from there. So if I want to round to 4 significant figures, then I need to see what 5 looks like. So if I've got 5 significant figures written like that, if I round that to 4, I can see that my 4th digit is now going to round up to a 1. If I want to round to 5, I have to write that other digit, which is a 6, that next digit. And so now to round this to 5 significant figures, I see it'll be a 21.4, and we've got an 096. Well, this is going to round to, I can't just make this be a 10. This is going to have to, it's going to round up the next thing. So it becomes a 4.10. There's my 5 significant figures. Notice how these two things are different. Here, this is unknown. Here, this is kind of a measured value. Yeah, it's the estimated digit, but it's still a measured value. So even though you might think of those as being the same number, it's just indicating a different degree of precision. Okay, if we want to go to 6 significant figures, I'm going to add in a 5. So now I see that that's going to be 21.4097. So there are my 6 significant figures. And finally, to get to 7, I'm going to have 21.4096 and 5. I got sloppy. Okay, hopefully that made sense to you guys. And looks like I forgot to get rid of a slide. I was cleaning this up. So I meant for that to go here. I believe, yes, I made it prettier. And then in addition to that, we've just done this section. In addition to that, we have now the question of rounding the following number to 4 significant figures. So if I've got this in scientific notation. If I want to round this to 4 significant figures, I don't care about this, right? I still have to keep that in there. I shouldn't have said I don't care about it. I have to keep that in there, but I'm not worried about that when counting my significant figures. This is what I use to count my significant figures. So 1, 2, 3, and 4 significant figures, but I look at my 5th one, and what does that mean? That means I round it up. 4.001 times 10 to the 5th is my answer. Okay, on this one, 375 point, hopefully you know the answer, 7, because that rounded up. And then finally, 897, I'm looking here, it's going to remain a 6, it's not going to go to a 7. So is that it? Am I done? Did I round correctly? No, I forgot something huge, and this is what people commonly miss. If you're rounding a large number that doesn't have decimal points, don't forget to put in the insignificant zeros as well. If I told you, yeah, you know, I know that I owe you $89,762 and $334. I know I owe you that much money, but I don't have exact change. Let me just round it. How about if I give you $8,976? No one would be pleased with that, right? So you need to make sure that you add in your insignificant zeros as well. I think I did this right. Yeah, there we go. So that would be our 4 significant figures in that case. Okay. Now we want to think about calculations with these. And when we go through doing mathematical operations with these things, we're going to see that the answer is it reflects the reliability of the least precise number. So in other words, an answer is no more precise than the least precise number that's used to get that answer. It's just like if you had a team that was racing and you must finish together, or you and your teammates must finish together. Well, how the time of that race is going to be dependent upon the slowest member of the team. So same sort of deal with your answers. It cannot be any more precise than the least precise measurement. So what we're going to see is that we have different rules for both addition, subtraction, and multiplication and division. There's two different sets of rules that we're going to use. And then here's another thing I want you guys to think about as you're reporting answers and going through and doing all of this math and chemistry, is that we do not use fractions. We use decimals. So what that means is if you happen to have a problem such as 10 divided by 3, the answer is 3.3. That's how we report our answer. So notice that that was two significant figures. The answer is not 3 1/3. So I just want to bring that up also. We do not use fractions in chemistry. So here's our example. Let's start with multiplication and division, which, to be honest, is used much, much, much more in our chemical calculations than addition and subtraction are. So what we end up seeing, if I were to sum this up, we just round to least number sig figs in given problem. All that means is you just need to know how to count significant figures. So if I'm trying to do this math operation, 13.1 times 1.2039, I have to look at this and say, okay, well, in this one, I've got 3 significant figures. In this one, I've got 5 significant figures. You're going to see that we are calculator people. You plug it in, your calculator spits out this big, big number. But you do not report all of those values because it's giving you a false sense of precision. You really do not have that much precision to be able to report it out that far past your decimal to those many significant figures. So instead, what you have to do is round to the least number of sig figs in your given problem. 3 is less than 5, so you round this to 3 sig figs. The rounded answer has 3 sig figs since 3 is the least number of sig figs in the given problem. That is your rule for multiplication and division. Really important that you know it. Addition and subtraction. It's important that you know this also. Instead of looking at number of sig figs in your given problem, we're thinking about the number of digits past the decimal. So in this case, we are going to round to least number digits past decimal in given problem. So here's my problem that I've got. In this case, I take these two things, these two values, and I add them together. I did it in my calculator. I was really lazy, and this is what my calculator spits out to me. Well, what I have to look at is that this number on top, 350.04, it is precise to 2 digits past the decimal point. I'm not looking at significant figures. I'm just looking at number of digits past the decimal point. This one is precise to no digits past the decimal point. So what that means is I have to round my answer to no digits past the decimal point. The answer can only be as precise as the least precise number in the operation. So that's what we end up seeing in that case. Now, what's typically going to happen, your most common problems that you're going to have in chemistry are just going to be a whole bunch of multiplication and division all lined up together. And here's what I want you guys to do on this. When doing multi-step calculations, keep at least one more significant figure in your intermediate results than are needed in your final answer. You round at the very end. Again, you're going to see that we're calculator people. I sit there and I plug the whole thing into my calculator. I never stop and write down anything intermediate answers. I just plug the whole thing in. At the very end, I round my answer. That is the easiest way, and it's really the most precise way to do it as well. Okay, so here we've got some math operations to do some calculations. I trust that you guys all know how to do these math operations, and in fact the number that your calculator gives you has been given here on your sheet of paper. One thing I do want to caution you on, if I were plugging this in, I would say this value times this value times this value divided by this value divided by this value. A lot of people say, once you've gotten these three, divided by this times this, remember that would throw this guy right back up into the numerator, and you want to make sure that you don't do that. You can get around that by using parentheses. If you wanted to say divided by parentheses 16.508 times 114.29 close parentheses, that's more work. Just get into the habit of whenever it's in the top, hit times, when it's in the bottom, hit divided by. So we have got that value given to us. I'm going to erase this so I can see. So in order to do this, I see that I have a multiplication division problem. Looks like right here I've got 4 significant figures, 4 significant figures, 3 significant figures, 5 significant figures, and 5 significant figures. And I know from all of my math training that 3 is the lowest number of all of those. So I am going to round my answer to 3 significant figures. 0.01, I almost said 69, but the correct answer would be 170. So I just took this and rounded, I looked at those 4 values and rounded that to 3 significant figures is what I did. Okay, next one, 4 significant, 3, so I'm going to take this and round it to 26500. Now notice that is the right answer. It is not okay to say 26500.0 because now with that decimal point present, that's saying that we actually have 6 significant figures instead of 3. So keep those things in mind. All right, different rules because we're adding and subtracting on these two. Here's what your calculator gives you. You're looking at a number, digits, past decimal, whereas in these you're looking at significant figures in the first two. So in the first one we've got 2 digits past the decimal, 1, 4, 2. So we're going to round this to 1 past the decimal and it becomes 10206.5. And last one on this. We've got 2 past the decimal, 3 past the decimal, so it becomes 42.36. Okay, hopefully you guys feel comfortable with that. All right, last little bit, scientific notation. And for this, what I want us to remember, I think you guys have worked with this in the past. Scientific notation, same thing as exponential notation, but this is a more common name for it. What you need is a coefficient between 1 and less than 10. So that's what you're doing. You're trying to change where that decimal is in order to make it be a number between 1 and less than 10. Then you're going to figure out how many places you move that decimal. And you're going to write it times 10 to something raised to that to a power equal to the number that you moved it. And what you have to remember is which direction that it moved. In my opinion, the way I think about this is that large numbers have positive exponents and small numbers have negative exponents. So if we wanted to go through this first one where it says to write this in scientific notation, well, my number between 1 and less than 10 is 6.74. And I'm going to say times 10 to the, oh, look at that. Is that a really, really big number or a really, really small number? And it is small. So that means that my power, my 10 raised to a certain power, is going to be a negative value. How many places do I have to move it? 1, 2, 3, 4, 8. So to the negative 8 is what we ended up doing. All right. Next one gives us a value, and I can see this is wrong. That's not even in scientific notation because this coefficient right here is not between 1 and less than 10. Instead, it's a really small number. So what I need to do, there's a couple different ways to handle this. I think really a fail-proof way to do this would be to first just put it into another form. And so in this case, we're going to say 0 point, I'm going to move it 9 places. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then I'm going to look at what I've got there, 0, 0, 0, 3, 7, 8. Now if I recount this, I see I'm going to take it and get it into a 3.78. That's between 1 and less than 10, times 10 raised to the, use a different color, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And notice that it's a really small number, so it's negative. I know a lot of you guys are going to be out there just saying, well, negative, it's going in this direction, and it's already in this direction, so you're just going to sit there and say 9 plus 1, 2, 3, 4, there's your 13. But this, and that's great, you know, if you want to do it that way, that's fabulous. There's no real rule on this. But this is a fail-proof way of doing it. If you first do your math like you see it, and then switch it to the correct way. All right, now we get to our calculations when using scientific notation. And I meant to change all of these to say scientific notation. But you guys probably caught that. Same thing. All right, here's what we're going to do. We know that when you multiply numbers in scientific notation, you add those exponents. When you divide, you subtract them. If they have the same exponents, the numbers can be added, you leave the exponents the same, etc. You know these rules. You guys have been in some pretty fancy math classes, so I know you know that stuff. And it's great to have an understanding of those rules. But in chemistry class, we really, really, really like our calculators. So get with a friend. If you miss this day, double check with a friend and make sure you really understand how to enter stuff into your calculator. But I'm going to look at that first example I have that says 9.6 times 10 to the negative fourth. 9.6 times 10 to the negative fourth, and we take that and we multiply that times something else. When I punch that into my calculator, what I'm going to punch in is the 9 button. Easy enough. The decimal button. The 6 button. Then I'm not ever going to punch in times 10 to the. Instead, I'm going to come over here, hit that second function key. Then I'm going to hit this key right here, which if you look at the second function, it says EE, that's exponents. So your comma that has the EE on top, so second function makes it go to the EE. By doing that, what that really does, that's like saying times 10 to the, and then our last thing we would say, since it's negative 4, you're going to find your negative button, which is right here, and then the 4. So I'm not going to spend more time on this video, but hopefully you guys feel comfortable with that. When you plug this stuff in, play with it on your own, and you should come up with 2.4 times 10 to the negative 8, 3.75 times 10 to the 8th. Notice in these cases, 2 sig figs, 2 sig figs, 2 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. So we've always got that matching. We're thinking about that as well. Even if your calculator gave you something different, you know to round that. That is it. Kind of a lengthy first lesson. Hope you guys enjoyed, and we'll be seeing you later. Thanks.